I'm going to be talking about additive manufacturing of cementitious materials. I like big words, and so I tried to cram as many of them into the title as possible. But basically, what we're going to be talking about is this concept of printing with concrete and bringing that technology into the classroom. And so I want to be sure to acknowledge my co-authors, Heather, who you just heard from James Madison. So she and I worked on both of these papers together. But then we also worked with Dan Blood from Valparaiso University, and then Shiho Kawashima from Columbia. All right, so I use this term additive manufacturing instead of 3D printing because additive manufacturing is really kind of the umbrella term that 3D printing falls under. And the emphasis here is this is not new technology. The new part of this is really the adaptation with concrete. And so with additive manufacturing, it's the converse of subtractive manufacturing, where you think about subtractive manufacturing, that's where we start with a large object and then we whittle away at it until we are left with what we want. Well, the other side is, well, we can just keep adding material until we get to the desired shape. And this is what civil engineers have always done. You think about building a structure, well, we pour the foundation. So we add material to get our foundation, we add material to get the structure, we add material to get to the facade. So this as a concept is nothing new to us. It's just the technology. And so with the, as I said, it's a blanket term, and there's a lot of different methods. So there's something called binder jetting, direct energy deposition, material extrusion, powder bed fusion, et cetera, et cetera. If any of these, if this is something you are looking to add to your class, I would encourage you to maybe think outside the box, and you can look at one of these other methods. But the one we'll focus on is going to be the material extrusion, and that's the one that we most commonly associate with 3D printing. So this concept, or this move to apply additive manufacturing techniques to concrete has really grown up in the last 5 to 10 years. Whereas the technology itself has been there for decades. It was only until recently that we said, hey, what if we start sending concrete through that machine, not just some type of plastic where we were making toys. And so this was spurred on by interest from both government agencies, so NASA. I saw some people from the Army Corps, and a lot of us have probably seen the pictures of the printed barracks from the Army Corps. NASA sponsored a university challenge where undergraduates and graduates work together to come up with a 3D printed habitat, which just wrapped up here in the last couple of years. There's multiple sessions on this topic that actually I think are going on right now, or maybe they were finished up this morning. So it is something that's gaining a lot of traction. And so really it boils down to, okay, if this is becoming a popular topic, and with how many different entities are really taking hold of this technology, it's safe to assume, it's safe to conclude that our students are going to be interacting with this technology at some point in their professional careers. And so this gives us an opportunity to start introducing it at the undergraduate and or graduate level. I'm not going to spend a lot of time redefining these. Matt did a great job kind of covering some of these pedagogical approaches, but these are the ones the authors and I kind of agreed on that would be the most appropriate avenue or vehicle to introduce this technology. So we're talking about inquiry, learning, experiential, problem-based, project-based. Really, the core commonality with a lot of these approaches is that we saw a real value in focusing on team type experiences, and of course the hands-on exploration with, I'm not going to say poorly designed problems, but just vague problems. So we want to go out and get you some experience with this new technology. All right, so really the first aspect that we focus on is teaming and dealing with ambiguous problems. As professors, very rarely do we ever really truly get pushed outside of our comfort zone into teaching something that really isn't in our wheelhouse. Sure, maybe you end up teaching statics, or you mechanics of materials, or some foundational course, but a lot of that type of stuff, well, we're practicing and we're doing on a regular basis. And so you might be really hesitant to say, well, I'm not an expert or a researcher in 3D printing or concrete pumping or anything like that. And so you might be hesitant to approach this because we don't have a set solution yet for this technology. And so how can we be an expert and then try to lead projects based on that? Well, the motivation should be, we want to introduce this new technology to students, but then we're also going to be promoting this idea of, we want them to be comfortable with ambiguity. And Heather mentioned it before, and that really be kind of, as we wrote this paper, I think that like in the back of my head was kind of the mantra of, we don't know where it's going to go. And if we want to prepare students to go out into the real world to deal with poorly defined problems, a lot of them get really excited about 3D printing. That part's easy. Getting them to then embrace that new technology and start applying it in a new area is an ambiguous problem. And so we encourage that exploration and really focus on self-instruction through a lot of this, because you, as the coordinator or mentor for the project, you may not have the answer, and that's okay. And so that's really the thing, that as you think about developing some of these a project based on concrete printing, it's okay to tell the students, I don't know where this is going to end up, and we're just going to have to be flexible as we work through the problem together. As I said, teaming was a really common aspect to a lot of these approaches. The team aspect gives them other people to rely on. A lot of even the subcategories under additive manufacturing really lend themselves well to a group working on them to be able to really create something appreciable as an outcome. So then the other thing we need to focus on as you start to think through this development of a project is just the engineering design process. Civil engineers as a whole generally don't focus on the first stages of design. So that conceptual design, going in, finding the problem, defining it, and trying to come up with some general concepts, the literature review. A lot of our programs focus on, okay, we're gonna, teach you this process to design a reinforced concrete beam. We're gonna teach you the process to design a concrete mix based on certain parameters. Oftentimes we don't necessarily close that loop. Maybe we do in senior year with maybe a senior capstone, where then we give them a little bit more open-endedness and make them apply different concepts. But a lot of times we kind of skip over that conceptual design. And so this is an opportunity to introduce this conceptual design phase at an earlier stage. And it hopefully will give you ideas to start introducing it, not just as seniors, but as juniors and sophomores. And I'm even working with a class where we have freshmen working on the conceptual design. Now, the other thing is, with this type of process, So because it's ambiguous, because we have a poorly defined problem statement, you need to reconsider your assessments. You cannot say, okay, everybody with a working prototype at the end gets an A, everybody who got close gets a B, so on and so forth. It has to be focused on that design process. So how well did they apply the process? Did they do some background reading, make a prototype, find that it failed, corrected for those failures, and started to move towards a solution? How well did they incorporate feedback? And this might be where you even introduce concepts of clients, right? So you can set yourself up as the professor, as the client who just wants this product, and they have to work with you to get you what you want. This falls very well with the Keen framework as well. If your university is partnered with them, those cards Heather was showing are from the Keen network as well. But the big thing with this, don't overwhelm your students. You really need to think about partitioning any type of 3D printing endeavor into some of these subcategories. If you just set out to say, we're going to make a concrete 3D printer with my senior design course, you're going to have a bit of an uphill battle. So I think Heather shared the experience where they had a senior design group work on it for 2 years, and they still didn't arrive at a working, functional concrete printer. I worked on it with my colleague at Valparaiso on a research level where we handpicked students. He brought in multi-disciplinary senior design groups, and we got a working printer, but that we still lacked a strong connection between that materials and actually getting it to print. And so these are not trivial things. And so it is okay to section off and focus your project on more of a very specific topic. And so I'm gonna highlight 2 of those, more on the rheology, and then also the computer generated coding and design. And so Shiho is working mostly with concrete rheology as it pertains to 3D printing. And so we kind of talked through some conceptual type approaches where they have to do some literature review, go into the lab and actually practice and do this, make adjustments, so on and so forth. This year with COVID, I found myself in a similar situation. So I came up with a project to try to engage all of my remote students, where I said, okay, go into your home and find whatever junk you can and make a concrete test to test the rheology for a concrete printer. And so it was really interesting, just kind of telling them this vague notion of go make up a concrete test based on what we've done in the lab as far as standard tests, based on what we've talked about in terms of demands of 3D printing. And so we had a whole range of these concepts that students actually dreamt up and applied to try to differentiate concrete mixes. And this was also an effective way to engage my distance students. The picture there, if I zoomed way out, you would see some pretty mountains in the background. Central Illinois, where I'm at, is not a mountainous area. He was doing this in Salt Lake City, Utah. And so he was doing this remotely. It was engaging him more, and he actually, emailed me saying how he had a really great time with this because it actually got him doing something, and they worked on this as a group to come up with these concepts and apply some of the knowledge in this new methodology. Some other things that have been done. So my colleague Dan, he's not a civil engineer. He's mechanical engineering. And at Valparaiso, they do a year-long capstone experience where the mechanicals and the electricals have to work together for the entire year. And so one year, they spent the whole year focused on this is the concrete extruder that we eventually came up with. And so this is all, it's computer numeric controlled. They came up with the programming, they built the circuit boards, they had to figure out how to extrude concrete and consistently, and yeah, it took a whole year for a team of students to come up with one aspect of the printer. And so this is where it's important to kind of think about maybe breaking off some of these smaller pieces. So one of the other concepts that he works with is in there, he teaches a finite element course where students learn about structural optimization or topology optimization. And in that, they actually had to go through the optimization, then transform their optimized model into G code, and then they printed it. Now they did this on a polymeric type printers, but then they actually had to take it into the lab then and test it. And so if you think about that concept where you're going from the theory of topology optimization all the way to, you know, bringing it in, connecting it with physical lab testing, and then also creating that bridge where they're also having to work with G code and think about extrusion and infills and things like this. They gained a very rich experience with additive manufacturing for this particular project. So the lessons learned, none of the authors have a full working concrete 3D printer that we actively work with every semester in our classes. Instead, we've broken it off into several different aspects, and we can focus on those aspects and don't trivialize those aspects. Just because we're civil engineers who are experts at concrete doesn't make us experts at concrete in a 3D printer. But we can rely on some of these other concepts from concrete pumping or concrete shotcreting or some other concept, and we can start to bridge that knowledge over to additive manufacturing. One of the big things we learned is students need a lot of hands-on, not only training, but then access to the components. A lot of this stuff they'll kind of learn as trial and error type of learning exercises, and that's okay. But one of the big things with these printers, I'm going to show you the big printer that I helped construct. It is dangerous, and so be sure that you don't slack off on the training when it comes time to have students working with the machines. And as I said, the last thing really is see where you can section off kind of reasonable bite-sized pieces for your class. The bigger the piece, maybe you want to look at a senior capstone class, or if you want to do a small slice, think about that maybe can be a semester project. Also, I'm going to follow it up here in my conclusions. Look at truly multidisciplinary teams. I think civil engineers and really all of us, we try to get away with this ABET's multidisciplinary teaming through saying, hey, we put a geotech with a structural engineer and that's a multidisciplinary team. With concrete printing, you actually have to go maybe across the hall, across the street to another building and find those mechanical engineers and electrical engineers and work on this together. You're going to gain a lot more traction with having some of that extra input into your projects, or if you want to get into research in this area. Focus on the concepts of design. That's going to be the big one. You're not going to be able to, and the project I had where we were looking at rheology, Some of the students' concrete tests weren't very effective, and that was the conclusion they came up with. And I had told them ahead of time, your assessment's going to be based on the process, not the end product. And so some of the picture I showed, that was a very successful type of test. Some of the others were not as good. And so you have to make sure your assessment is calibrated to handle success and failure. And with that, I think I'm a little bit over time, but I'd be happy to answer any questions that you have or talk about it some more.